Hello. I'm ready to tackle quest 14 of everybody codes. Got my template ready to go. All my tests are failing because there's no code in there, but I am ready to go. So here I go. Okay, interesting. So we're doing movement. Okay, so movement and directions. For the growth plan, the height of a mature plant is 7. As the highest part is 7 segments above ground level. Okay, so it's just moving directions. So const lock equals x0, y0. This does seem directional though, right? Let me see. Up, right, and then once I'm facing right, it will be down. Then I go left. Okay, so it's not directional, it's just coordinate based. Okay, got that. Let's do that. Const changes equals notes. And split on the comma dot map thing const dir equals thing 0 const change equals thing that selects 1. Convert that back to a number. So now I'm just going to convert this based on that. So we have 4 of them, right? So switch dir case u return. So up, I guess I'm going to cause that a positive y. So it's 0 and then change x0 y0 case r. So that is change 0, and I'm going to write the other, I think this many. Okay, formatting has just made my life really hard. But yeah, so we have up, right, down, left. I mean, there's only 4 of them, so shouldn't need to be that many. Okay, so up and down are 0 minus change. Left is minus change. Boom, we have that. URDL, and now we're just going to do this thing. So for const change of changes, it's going to be, okay, so it's con xc equals change 0, right? This is an array of things. Yes. Const yc equals change 1, x plus, well, walk.x plus equals xc, and then yc. I can see a third dimension getting added to this, or something else I'm going to do. Return, I need to get the highest I've ever gotten, right? The highest part is 7 segments above ground, so m max y equals number dot min. And then I'll just do it at the each max y equals math dot max. Don't alt that. Max y, location y. You know, let's do it in all the places. Max y, I think that's correct. Boom, we got it. Give me my notes. Okay, it's a few more changes. Cannot read properties of thing 0. Ah, did I goof? No, this is correct. Cannot read 0. So I guess I gotta look at my changes, because they got parsed wrongly. A lot of undefineds. Oh, we have F. We have other directions. For the sake, there are no F and B. Oh, forward and backward. Forward and backward. Oh, this is in 3-dimensional space. It just didn't give me the things. Okay. Up, right, down, left, forward, and backward. So I have X and I have Y. I don't have Z. Okay, so I'm gonna put Z in the wrong place, or from a dimensionality standpoint, maybe the wrong place. I'm gonna call it depth. I know it's Z, but I'm just doing the thing. Depth plus equal DC. DC, now let's add 2 more cases, right? So it's forward and back, which, I mean, both you turn back to 0. I'm just gonna go forward, doing it away from me. So it's negative change, and back is positive change. It's gonna be fun to visualize. Yeah, let's not worry about formatting that. Still work on example, work on new one. That's a number. Boom, okay. Can be achieved by planning several simultaneously. Separate lines starts in the same segment. Does not affect. Calculate the number of unique segments. The heck do you mean by unique segments? Oh, it's just literally places Ben. Okay, we got this. Don't have a plan necessarily for that, but we can do that. Let me solve quest 2, solve quest 2. Be my example input. There you go. You're saying this is 32 unique segments, which if I just 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. So was it 6 times 5? 30 plus 2. Okay, so it's literally unique places we've been. So I'll need to keep a tracked map of all places I've been. I got that. Let's do it. Solve quest 2. Changes is notes dot split new line dot map L. Then it's going to be L split. I don't need to log this no more. Changes. And I just need to keep track of all locations been. Let visited equals congratulations. I'll just make this a set. We don't need any association here. There we go. And then it is for changes of changes is, again, the best variable names you've ever seen. I don't think I need this max X and Y thing. I do need to name things correctly. Pre and post, so I'm just going to do the badness again. Then what is that? Object, well, I need visited signs, really. Okay, good. So everywhere I go, I just need to add it to the visited. Add location walk X plus lock.y plus lock.depth. And you just do it again down here so we can't miss you. Okay, yeah, part 1 still does great. Got a console log in there I don't need. Part 2, only 13. First branch produces, ooh, location needs to be reset, right? So for each one, boom, location starts here. Let's fix that. Don't know why we got less. If anything, I would have expected more, but okay. Expecting 32, getting 13. First one contains 24, second one contains 14. I'm parsing things correctly. Some overlap, so 32 unique segments. Okay, I'm not seeing that. XY depth pre and post for change of changes. Changes are being generated here. Okay, I could have just been parsing it wrong. Let me looky-loo. Changes, 2 arrays of positional changes. Yeah, and they're all, you know. Okay, let me look. 5, 3, minus 2, minus 5. 5, 3, minus 2, minus 5. 4, 5, 2. 4, 5, 2. Yeah, they're all in there. Visited, I'm adding where I am. I'm adding where I end up. Yeah, I am doing on the location, because that's my current place for change of changes. Ooh, this has been broken the entire time. Don't know how that was working. Slightly concerning. Wait, what? Okay, I'm gonna go back and try and change that to see what goof that was about. Sure, not gonna question it. Let's get rid of that log for my running sake. Changes is for changes of changes is location start here. We move. Okay, they're talking about simultaneously. Do I need to do that? Some segments may choke appear in multiple branches. The mature plant consists each having at least one additional segment fused on one of its sides. Yeah, this seems perfectly the same. I can visualize this. I don't want to, but I can visualize this. Let me just look at visited, see if I can spot something wrong. Okay, well, let me back in. You only visit 13. Do we at least have the trunk? So X0 going up to Y. No depth. Wait, 13 was one of them, right? 14 unique segments. For changes. Okay, I need to go into here. Stop. It's something dumb, I can tell it. I can tell I've done something idiotic. Yeah, so for changes, where is it? There we go. 5, 3, negative 2, minus 5. And then the other one. Yeah. And my new location, and you go places. Oh, it's not saying every place you've been. Right. Whoops. This is multiple distances, so I'm only tracking the ends and the beginnings, not the lines in between. Okay, I see what I've done here. Yeah, it's basically a for loop, and inside the for loop I do all three of these. So, for let equals 0 less than xc. And come on, xc, xc, x plus plus. And then we do this of, hey, let's add where we were, where we are. Again, most expensive way of doing this, block x plus plus. Then we do that 2 more times. We don't do these. I think I can just do yc, dc, then it'll be y plus plus. Well, it'll be also not depth plus plus. It'll be based on if it's positive or negative. Plus equal math dot sine xc. If it's negative, I need to go the other way. Boy, me choosing these characters really made it hard on myself. And then this one, just grab it to me, the y, depth, dc, I think that'll suffice. Dang it, 21. So these could be wrong. I'm getting better. But these could be wrong. So if I do the exact same changes above, I'll know if it's wrong, because it'll go the right places. Do that. Just drop the visited logic. Alright, so if we drop these, drop these, drop these, we'll see if that movement is actually a functional. No, it's bad. Okay, I goofed. I think... yeah, this appears to be correct. So x goes to xc, y goes to yc, d goes to dc. Am I just off by 1? Is that it? No. I've just goofed it in some way. X, xc, y, yc, depth, dc. So I'm doing the sign trick. Maybe I just need to not do this. Plus equal, I see, greater than 0, 1, minus 1. I'm just re-implementing math sign, I feel like, but nope. X, Y, depth. XC, YC, DC. You do it that many times. Okay, I am doing a less than or equal to now. I made 2 changes and expected to see something happen. Okay, I gotta go in there, unfortunately. Let me in. Okay, let's jump straight into here our changes. Okay, so we have 3 changes. Yeah. YC is the main one. Should I go? I should go to Y5. Let's do this. 2, 3, 5. I did it. Crazy. It's failing by saying I'm going to 9. Huh. Yeah, sure, might as well just go there anyway. So yeah, now we're at XC, so we're going to go to X3. I went too fast. Show me what I got. Come on. There we go. And if I skip down there, -2, so now we're going to go down. So we're going to go to Y3. Oh, yeah. It was me. I was the goof. Okay, that's literally what I need to do. I need to just math abs these. I can do that. Just grab the less than sign. I'm assuming this was the problem and not anything else. 32, 33. Ooh. Interesting. So it's probably because I'm adding 0, 0. So I just -1 this. Feels like a cheat. But we'll see if it works on the real. Boom, look at all them branches branching. It's a lot of additions, but we'll see about it. That's a number, and it could be off by 1. Boom, okay. Amber leaf tree, special sap. Last segment of each branch forms a leaf. Has as many leaves as there are defined branch lines. All segments directly above the starting position constitute the main trunk. Tap. Okay, sure. Let's start on this. Put that back in. Grab my example. I think I'll make this a 3 because I'm feeling it. Okay, we have 2 examples. So 5 is this one. Example 2, more advanced. Just got me worried. Okay, might as well grab my input now. Okay, let me start understanding what's going on here. So, the main trunk composes of all of this. A sample place to extract is one segment to the left of the top leaf. The plant has 2 leaves. These are leaves because they are where the last ones ended. Up 5, right 3. Oh, up 5, right 3, down 2. Left 5, up 4, right 5, down 2. So my leaf is right here, and this one is somewhere else. Okay, so the leaves are the last place visited. So I need to keep track of that, your last location. Got you. One segment to the left of the top leaf. 1 segment away from the top leaf and 4 from the bottom leaf. Okay, so I need to re-extrapolate this logic for this. Okay, the last segment of each branch forms a leaf, has as many leaves as our defined branch lines, assuming they do not overlap. So if 2 of them end on the same segment, you don't get 2 leaves in one space. Okay, tap into a segment of the main trunk, ensuring the total distance to all the leaves combined is minimized. The sum of all distances indicate level of sap murkiness. Okay, so I'm like, hey, I have all of these ones in the main trunk. Get the least distance to all of them. Well, to the leaves. Okay, so first thing I just need to get all the leaves. So I see enough. I can start on it. Boop, boop, boop. Quest 3. And then I just need to keep track not of the visited, cost leaves, which is a new set in my mind. And instead of keeping track of visited, I think, let me think about, yeah, basically anyone that are over the main branch. So where I have an x of 0 and a depth of 0, cost main new set x0, so basically main segment wise. Okay, so if any point it's basically good, then we add it. Let me get rid of these max y's, these manuals, those, because wherever we end, leaves add. Okay, I could have used one of them. I'll take that to the future. Leaves add. So boom, we found all our leaves. They are uniquely being gone away with. Add if main segment if, and let's move that into this because it's function dependent. Lock.x, so x is left and right, equals 0, and lock.depth equals 0. Main segment wise add lock.y. So these are all my considerations. There we go. And I want to do that every time we make a change and before we make a change too. So there. A little better. Again, we have extras. It's all fine. We don't care about visited. We don't use that anymore. But now we have all the potentials and we need to do that math. Okay. Total distance to all the leaves combined is minimized. So let best equals math number dot, we're going for the smallest, so we'll go for the math for cost y of main segment y's. Let distances equals here. Then we need to go through all the leaves and count all the distances, and then what? Sum, average, minimize, do some stuff on it for cost raw leaf of leaves. Cost, what is this? X on depth equals raw leaf dot split, not specific, by the bar dot map number. Types have abandoned me. What are leaves? Leaves are a set of unknown. No, they aren't. They're a set of strings. And main segments, your set of numbers. Boom, got that. So we have that. What's the distance calculation? We do Manhattan or the other one? A sample place is one segment to the left of the top leaf. So we're trying this one. 1 from the top leaf, 4 from that one. How did you calculate 4? I think that's Manhattan distance. Oh hey, that's actually not too bad. I'm gonna use that partially. Manhattan distance, XY depth x1, well, I'm trying to think how I want to pass this. Sure, I'll just take that as is. So we have this, and then we have my current, which is that y, but what's my x and my depth? They're both 0. Okay, so I think I can just say let total distance equals 0 and just be, hey, let's add total dist plus equal Manhattan distance from my current position, which is x of 0, y of sy, depth of 0, then xy depth, just need to make this an sy, then best equals math.min best total dist. And do I return the distance, or am I returning the thing? Well, the murkiness level is the distance. Okay, so I'm returning that. Okay, that was a lot of typing, not a lot of testing. Let's find out. Okay. No, I'm off by 1. Yikes. 20 segments above the ground. Lowest possible murkiness level 46. So I do need to log when I find the next one and be like, hey, you're the thing. If total dist less than best equals dist, and then console log sy of like, hey, who just won? So we're not tracking that. 21 is better than 20 apparently. I am doing the uniqueness on my thing. My Manhattan wrong. It is also an off by 1. So I'm gonna go for this actually. Answer length. First answer. Ooh, okay, so I'm really off. It's just not exposing itself in the example, unfortunately. Is it 46? Or was it supposed to be 46? 20 segments above the ground. Lowest possible murkiness level 46. Is there something here? Okay, so something about overlapping, right? The sum of these distances indicate the murkiness. Oh, this is pathfinding. How many segments it takes to travel from the tapped segment to the leaf. There could be air gaps. Interesting. So I do have to generate this and then pathfinding my way from it to it. Interesting. A 3-dimensional Dijkstra's would be maybe. But the thing is, it's for every segment, right? So it depends on which I have more of. Segments 1, 2, 3, 4. I mean, we have less than 20 here. So it might be better to make sense how many segments. This one says up 100, so that's 100 segments, all the bottom of which are gonna fail. We can do some early failing, that's an option. If it ever goes above, let's implement that. If total dist greater than best or equal to greater than, we'll stop that. It's not really gonna help us with the main thing, but it's there. Don't debug the test, I don't need to see it. Okay, so distance between segments, which means we need... Is it between them, or do I have to follow them? All adjacent segments are connected, even if they've grown each... Okay, right. So, not diagonal, so they mentioned that because there is the pathfinding here. Okay, so it's not Manhattan distance, it's... distance between, and it is still distance between these two, just calculate it a different way. So I'm gonna comment that. I want to see how many, I want to see stuff. Show me stuff. I'm not looking at that one. It would help to debug the correct test. Okay, so we have 110 main segments, 20 leaves. So it will literally be less work to go from the leaves to everything else with Dijkstra's there on the third dimension. So let's go pull that out. Yep. Where do I put this? I put that right there. Now I need to watch out. So I just have from, I have to, I have weight, I haven't implemented that there. The distance is literally just going to be a bunch of ones. Okay, I think this is good. This doesn't need any changing. I do need to generate the graph, so which means I need to track everywhere I've been, which just means I need to keep all locations. And then I need to keep the relative to get to neighboring locations. So usually this would be a 2D. So I just go for a 3D. Const world equals x, y, depth. That's the way I'm going to do this. So record, string, record, string, record, string, 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 string. I think that would be the way I've done it, because a two-dimensional would be how many are we adding? You know, I don't want to go super optimized on this. Let's just say const bin equals new set string, because this could be really easy for all we know. Bin add, then I have to have this bit here. Boop, boop, boop. There we go. Before, after every change, after the file change for good luck. We don't need that one. Yeah, I think that is sufficient. Yeah, let's just see how many places we've been. Worst case scenario. 6,000. That's another thing. Okay, we can do that. Yeah, so now we just need to generate a graph from every position to every other position. Okay, so that is that's going to be somewhat expensive. Trying to think, it wouldn't even be worth it to try and build the graph as it's branching out, because things touch each other at different times. So const graph equals, hey look, a giant object, or const a of bin, const directions, const directions equals, and it's 6 of them. So 1, 2, 3, 4, 5, 6. I lost all my commas. Right. So a left, right, up, down, forward, back. I'm talking about a cube, so yeah, the cube has 6 phases. I'm just losing my mind. For const dir of directions, and I'm gonna need this pulled out. X, Y, depth. Gonna go steal the code I did from over here. Yoink. Love it, which is, I guess, place. I don't know. Const and X and Y and depth. And that will be X plus, I guess I should break this out. XO YO DO plus XO Y. Whoa. Y plus YOD. Come on. D plus DO. Okay, I know it's angry because of TypeScript. Is that right? What is going on here? Oh, apparently DO is forbidden. Sure. Yeah, basically I just need to find if you exist. Const key equals an x plus, let's just do the array. It's getting a lot tedious typing this out, that's why. If bin has key, then I need to basically, I think it's gonna be fine because I can do a process too, but no, I'm just gonna do it from and to and let the other one be generated back. So let's do this. So let's say graph x, if x and graph x equals thing, if not y and graph x y equals thing, then is graph x y. Oh boy. The depth equals, and this is the new one I'm going to, so key. I feel like I missed something there. Yeah, that's not how we build the dumb graph. It's just coordinate to coordinate. I don't need the dimensionality. I mix my things up. From key, which is place, equals from this to this with what weight? My weight is always 1, so maybe I don't even need to. I'm gonna do it anyway. Which is technically a check way up here, so let's do that. Place graph, place equals there. Now I can say graph place key equals a 1. Boom, there we go, we have our graph. And now I need to generate distance between, which is going for each leaf and being like, hey, here are my graphs. So const leaf distances, I think we'll just do this in memory. So for const leaves, leaf distances leaf equals Dijkstra from graph starting at leaf, which is not a number, it's a string, but that's okay. That should be able to handle it. That part is a number. There you go, it's the number 1. Which, again, graph doesn't need to support this. You can just be a literal 1, but we're here now. And now we have leaf distances. So now we do this, which is going to be our cool new one. Distance between P0, P1. And let me go back to the drawing. Distance from the leaf to the thing. So let's do trunk leaf. So it'd be leaf distances, and then it'd be the trunk position, but it'd be trunk.join with this. So I'd be returning that. So my memory might just die. But I'm feeling pretty good about this. Let's see if it works on the examples, thankfully. Yeah, I don't like that. So I don't have anything here? What's going on? Oh, I didn't even use the leaf. Oh, leaf distances. A leaf. Yeah, you need that to be there first, buddy. Okay, good. Okay, good. Time to kill my computer. It's a dying. Oh no. Boom. And we got it. Woo! That was a good one. Loved it. Okay, let me shove that correct answer in there and give us a full run. And run. Beautiful. Okay, I'm gonna clean up that console. Yeah, we'll do the entirety of it. And we'll commit this. Add initial 14 solution. Do I have something like git ignore? No, nothing relevant. And let's walk through what the actual challenge was. So, these are palm trees. Yeah, they do, I guess, dimensionally look like palm trees with their tall trunks. Didn't even consider it. So, apparently this was a daily growing segment, but we have a list of absolute growth directions and growth amounts as a list, including forward and backwards. So it's a three-dimensional growing thing. As it grows, you track where it's grown, and you can, if you track it, it looks like this pretty picture. Part one is to just see how tall it grew. So the tallest it was ever been. Part two is to see the number of unique trunks or segments. And this is tougher because it adds two of them. So you have two simultaneous growths from the same coordinate. They can grow on top of each other, which at that point they just merge and they don't do anything. They can also grow in two unique places. So the combination of all their coordinates results in, for example, 32 unique growth places. Part 3 was tracking the end positions of each of them. So like where each of these segments end, that is considered where a leaf is. And then calculating the position on the trunk, which is this central spine of segments, that is closest to all of these leaves. Now, not closest geographically, but closest as in the shortest path from that central trunk to that leaf through, where is it? Through the actual tree itself. So there could be air gaps in here. You cannot go through air gaps. Where is the thing? And yeah, you get 6 sides, not diagonals. And yeah, that was basically it. Relatively straightforward logistically, I guess. Like not 15 different things you need to juggle or do, but still pretty good. I like it. Yeah, that's the main challenge. Now it is a refactoring time. So, I did do X, Y, and depth, which is fine. I like this. I'm trying to think if I can mash all 3 into one. I believe I can. It would unnecessarily increase the runtime of some of them, because for each one you're only looking for a certain thing, so like you don't need to record as much. But doesn't mean we can't overlap some things. Yep, I'm just getting rid of all of this. Actually, yeah. Start by just cleaning up the existing functions. Yeah, changes into these. Let's see what they logistically called them, what the lore says these are. Growth. Okay, so these are growths. So let's start with that. Let's get some parsing going. Get that functionalized away. Parse growths, notes, string. I think it's the changes is what I'm gonna take. There we go. Return. And right, so this is, we're doing this. This is the first thing we're really going to decide on. How I'm going to want all of this represented. So like I have tuples, I have objects. I think I will need to keep I was trying to think of like a mathematical way to smash all three into one number, and while I can do that, that would require me knowing the maximum of at least 2 dimensions. I don't think I'm going to be able to get that up front without a bunch of pre-processing, so I don't think I'm going to be able to fancify that away. As for how I represent, though, x, y, and depth, x, y, z, right, so y, x, z. The thing is, I'm always getting these wrong because I use Blender and Godot and what the heck is that roll? Okay, so Z and X are the ones facing me, Y is my depth. But this one says X. There we go. Okay, yeah, I'm just gonna do it with my own thing. I don't think I'll even call it X, Y, and depth. I think I'll just go left, right, or yeah, this one's height for sure. I think, could I just do that if the one's happy? Nice. Okay. So yeah, X change, height change, depth change. Yep, that's what I'm going with. Now, do I want to keep them in a tuple or extract them? I'll leave them in a tuple. It lets me name them as I wish. I will move these around a bit to get them near their siblings. So the ups and the downs, the rights and the left, the forward and the backs. I like that. Switch case, perfectly valid. I love it. Changes. I just changed the wrong one, dang it. This whole cool function, I was like, hey, I'm gonna not update the function. There we go. Okay, so parse growths. So we have parse growths notes, and we only have one, so there you go. Then we have growth. There we go. Let's drop this. Now for part 1, I don't actually need these. I can just move, which, if anything, is a better. Now, for part 1, I don't even think I need depth and X, right? I just need the height. So, I'm just going to be lazy and just, like, not do those. We're going to destructure them here. Height change. HC, there you go. And we don't need this many freaking maxes. So I think we'll start max to, well, we'll start at location.height, and then we just do the after calculation, like so. I think that makes quest, or part 1, perfectly happy. Loving it. So I think we can move this one down. Oops, or that one around. Sure, max Y is the thing we're doing. Well, if we could do some crazy bad stuff, let's do bad stuff. Yeah. No one's going to stop me. This could be a reduce. I'm gonna embrace the darkness, embrace the unreadability. So, see? Oh yeah. Nobody's gonna be able to read this code. Yeah. Now, we do have this other thing, this location being around, but it's fine. There we go. Nobody reads this code. Okay, now let's do this a bit again. Do const equals parse growths notes. Put an equal sign there. Growths for growth of this for change, which I will destructure into XC, YC, and DC right now. If we keep track of everywhere we've been, important thing to do, big fan of it. Let's at least rename this one to HC. It's more accurate. I don't like this math abs, that's an expensive calc. Okay, let's worry about this. So let's start with visited, add. Right, this is the first one we're adding this thing. So const lock to key equals lock or location, which is, I don't have a type for that, but I will right now. And then just concatenate these little pipes. Type lock equals x number, height number, depth number. Love it. Especially as that allows me to do things typed. So visited, so just a set of strings. Don't you worry about it. Boom, I love that. Okay, so visited, add a lock to key lock. Okay, so we have our initial. We want to just add every change. So the after will suffice, like so. Instead of doing this the long way, we'll use a cool function. Lock to key lock. Big fan. Think that works for 2. That it does. I can see this being functionalized away. So it's basically move n times cross thing. Let's see if I can write that. Let me write it in here first. Function move thing. Yeah, so thing will be direction. So we'll want key of lock, I guess. Then it'll be amount number. Yeah, I think that'll be enough. And then it's basically this. Const times equals math abs amount. I don't really like amount. I like the word change. Then it'll be math.sign change, I guess, and direction is what I'm changing. So I like that. I know what key of is, computer. Okay, so let's try and use this, and I'll think of a really cool name for it. XC. I like it. Let's do the other ones. Height. Oh. Depth. HC. DC. Kill the rest of these. Oh, look how much easier that is to read. I love it. Now I need to think of a really good name for these. Grow in direction. Grow in direction. Sure. Grow in direction X by this many. I'm fine with that, yeah. I can see this being an object would make this a little easier, but we're living fine as is. Move that up there. I think this needs to be here to access a location. But we will... also needs to access the visited, right? So grow in direction. Right, so we need these things. I mean, I can just pass these arguments. Grow what in what direction? Grow lock in the X direction, so I like putting this one first. And then we'll keep visited last, because I like it. Now let's reorder that appropriately. Nice. Okay, I like this. And for 3, Dijkstra is going to Dijkstra. Let's do this. Parse growth notes. Growths. There we go. We have main segments. Let's just call it trunk heights. There we go. Drop the world. Drop this. This is visited. Yeah, we have some good things to do there. Drop that. And yeah, we'll optimize the Dijkstra to use a little less information. Let's rename growth. Let's destructure that. XC, YC, DC. Rename this to height. Again, some optimizations. A little repetition going on here, but that's okay. And then add if main segment. Okay. So it's kind of a thing we want to do after every, not just whatever. So after every change, we want to do this, and then we want to do something else with our location. So let's say on grow. Let's take a little function, which will be the new location lock, and then you'll just do something with it. On grow lock. Congratulations, you grew. And yeah, this is optional, so let's, what is it? I like that, right? There we go. Now let's call this add lock to visited lock, visited add a lock to key lock, which I can just do this right here now. Add a lock to visited lock, boom. Add lock. Ooh, I love this. This looks great now. Come on. Don't need all these extra lines. I'm loving this. Make sure 2's still good. It is. Yes, we're spending a little bit more by calling a method. It's fine. Okay, so I think I want to bring some of these things down here. For growth and growth, lock, do all the things. Let's bring this down. Yeah, so we're bringing that over too. Again, we're seeing a lot of reusability as we write this. Boop. Okay, so we have that happening. Let's call it on grow lock. So we're doing that, and then we have a conditional bit here. There we go. Also do that. We love it. I think that's it. Yeah, the rest of this is just what I've had above. So I can drop that, and that should be fine as is. No, I broke it. Oh, it's not doing the thing. For growth of growth, X. Ooh, right. Height. Is that? Man, I made a few changes. Interesting. Okay, we will pretend that one doesn't exist. And pretend that doesn't exist, right? Let's go back, make sure we can restore. to a happy life. Okay. So let's see, for location 000, add domain segment. Basically every time we think about touching it, also adding the visited, also adding leaves. Hey, I forgot that. So once you're done with all your growth, leaves.add lock to key lock. It's kind of an important part, you know. Them leaves, not just a tiny important part. Okay, I'm loving it. So on grow lock. So I'm just rename this to add to and main trunk. That's what happens. It's gonna look so good when I make it look better because I'm seeing the repetition already. Well, I could do some really weird stuff where you're just passing an array of functions. Let's not get too fancy yet. Directions as const. I think that is good. It's what I want. Then we have our cool graph, which there's room for optimization here. It would require a tweak to Dijkstra's, but that is sufficient. Because the thing is, we're saying, okay, you all have a weight of 1. That's not information that is unique or changing in any way whatsoever. So what I'm thinking is, instead of making this, what is it, an object, we can make this a better data structure. At least we can make this a list. And then we can just be like, hey, dot push list. Well, not push that, push key. Which makes my graph a little different, because it's now just a string array. And TypeScript will yell at me, that's good. So times to node plus 1. That's all it is. Alright, so it's time I took to get to where I am, plus 1. Yeah, that's all it is. No, I broke it. Okay, maybe it's a little more complicated than that. Times to the neighbor, which is infinity, where I'm at right now, plus 1. These are all just plus 1s. Graph node. How much does it take to get to the neighbor? 1. This always evaluates to 1. So I changed maybe more than one thing. Is that what's up? Ooh, I did in on of for neighbor of. I don't see how that's gonna do it differently, honestly. Never mind, that was exactly what we needed to do. Oh, because n was the indexes and I used the key as a thing, right? Okay, makes complete sense. Yeah, I think that's exactly what we want. Yeah, maybe some more I can squeeze out if I wanted to. I'm not in the mood to squeeze it though. Okay, so we have our graph. We have every place we visited. If we haven't built the graph, add it. Let's make another key to lock. Cause key to lock equals key string. Well, we'll need a few more lines than that. Const x, y, or x height, and then what is it? Depth. Key dot split on that map number. Now I can return the object like that. X height depth. Now I can use that in all the cool places. This is the first time I've actually had a chance to use it. So const from equals key to lock, which is place. I guess, what is this? Const 2 equals x from dot x plus nx height from dot height plus nh, which I don't have written, but I will in a second. Depth from dot depth plus nd, so nd e and nh, because these aren't y's anymore. So height offset. Great, we drop that. We have our 2's, which is, oh, I've been using the wrong ones. Okay, that's fine. Key equals const key lock to key, which I'll pass it to once that gets working. XO HO and then do. There we go, much better. If visited has, basically you're a neighbor, then push it. Okay, I like this. Why did this have to be, nope. Apparently do, oh, it's do while loop. Let's go back to the changes then. So XC, HC, DC, there we go. Make a new 2, which we literally only need for the key generation, so let's inline that. Go, if we haven't seen before. So let's call this from key from lock, which I'm going to need no matter what, so let's just go ahead and always bring it. And then rename it to key. There we go. And if visited, we visited that one. Da 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 da. We're great. Leaf distances. Yeah, let's get some types actually going in here. Record string array. There we go. Leaf distances. Record string number. Love it. I think this can be cleaned up too. Yeah, this could be a fancy reduce, but I ain't gonna go for that. Right, so we have the trunk height. Let's put that in there. Total distance, and we'll just do this here. Best equals math dot min. Best total distance. Let's rename that to, not there, least distance. There we go. Okay, now we have for raw leaf of leaves, let's just call it leaf of leaves. Convert this into numbers, and then we pass both of these, just get converted back to a key. So you can just keep your key. Alright, let's say leaf is a string. Alright, we don't need you to turn back into a thing. Now trunk, yeah, we don't, I mean it's a set position, but it's being generated each time. We can generate that up here. So const trunk lock, which we don't need the location, we need the key. So key equals lock to key x0 height trunk height depth 0. There we go. When we have a trunk key, that's what this needs. String, which is right there. Now I've made quite a few changes. Let's make sure this still works. It does, like a charm. Yeah, so we don't even need the height, so we just need the keys. Let's inline this bit here. Trunk key. Yeah, leaf distances. Distance from leaf. Distance from leaves. From this to that, you got the distance. I like it. I think this is the best way of doing it. Now, I have an early break there. Big fan of that. Let's separate that a little bit. I'm thinking about the fact that trunk height is used literally once for the trunk key. Can I just put that into trunk heights? So it'll be trunk keys instead of trunk heights, and then I can directly use that here. I'm trying to think. So we'd basically be spending over triple the amount of memory to save this one operation, which we would have to do anyway up there. So it's a waste of memory for not much gain performance-wise. Okay. I'm pretty happy with this. Yeah, I think this part we can do some work on. So let's do that work on it. It's basically this entire code block. You can be a thing. So grow growths, I guess. Function grow growths. Put that there. Let's see what we need. There we go. Growths, which is what do we call this type? Return type. Return type of parse growths. There we go. Being lazy. On grow block, do something, and then on finished grow, on final grow, on grow end implies a grow start, on growth end. Okay, let's see about this. So we'll count this as an on grow lock, well, conditionally, of course. Boop. Well, question mark dot. There we go. We'll just pass these straight through. On growth end question mark dot lock. Okay, so we have grow growths. Let's see if we can use that in the one we took it from. So grow growths on grow, which is do this, and then locked key leaves add. So lock leaves add lock to key lock. Boom, I think that's it. Let's see if that works. This is for 3, so go in 3 land. Loving it. Haven't ran the notes in a while. Let's make sure they didn't break. Loving it. Even we got faster, which imagine that. Now, I like this. I'm going to reuse this down here. Grow growths. Ugh, spell the word correctly. Growths. Add, what's the second one? Add lock to visit. No, it's growths, not all this. There we go. Part 2, part 1, loving it. That's not actually part 1. Let's do part 1, which, and we kind of cheaped out and we were like, hey, let's not do things. We could, though. I think I'm going to. I just want to, I think, upgrade this a little bit. I really liked the idea of passing multiple on grows. So let's swap this around on growth end, and then here, I don't know the way to do this. I mean, I've never done it this way before. Rest parameter must be of array type, so if I just swap these, and hey look, it's an array of functions. Boom, got it. on grow for each grow on grow lock. And we just pass all the on grows to this thing, which you are also going to take an array of these functions, because I'm being bad. No one's gonna stop me. Grows. Yeah, let's at least call these ones plural to make this typing a little easier. Boop. There we go. So for each on grows, just call the thing. And now we can pass those straight on. On grows. Oh, we'll need to spread them. There we go. Okay, I'm liking this so far. I think this is going to get absorbed into here once I make one more change. But before I do, I want to make sure everything is still... Nope, I goofed it. There was a parameter order change that I didn't transcribe all the way. Let's do that. No. So grow growths, you have on growth end, and then you have all of your on grows. I don't know how conditionals be a little weird. Right, yeah, that's why they're being weird, because there's nothing in that slot. Call you a no-op, and I'll make a no-op in a moment. No op equals void. Give me my thing. There we go. I think that will make it happy. Nope. Oh, I've lost definition. Okay, fine. I have to really define you. Okay, good enough. So yeah, instead of you just being this, I'm just gonna set you. Think we can do that there legally? Yeah, you always have to pass something, so it's no longer conditional. That'll be fine. Okay, 1, 2, they're all still working good. I'm gonna do this growth parsing to be different. So parse growths, let's get you doing something else. So instead of all these arrays, you're gonna return a coolia little object. X is that. Okay, there's no easy way around this. Boop, 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 boop. Height is that, and then depth will be right over here. Oh no, it was goofed it. It's okay, I'm still... No, I'm not. This was depth. Basically, it's just an array of lock. Well, it's an array of locks. Okay, I love it. And now we can parentheses height. Boom, we just add your height right here. Love it. This is where the fun begins, where we have x height depth, which yeah, we're just gonna put right here, x height depth. Not much changes, I know, but this is where I can make it even less readable. So for change of growth, for const key and change. Oh yeah. And TypeScript should pick this up. If it's not, it's really sad. Change key. It's dumb. As key of block. Aha. We're being so bad. Which means now, if it's a one call function, it can go in here. So let's do this. Let's call this amount. Change amount. Come on, I'm getting there. And rename this from key. There we go. Draw up that. And then const change amount equals change key. Could do an entries here. I will. Direction is change key, which needs the typing, or it's not. It's really smart. Nope, it's really dumb, actually. Good enough. Oh, loving it. On grows for each. On grows for each. Let's do change times change count. Change amount, which I use there. I'm using the word change a whole lot. It's not the worst. I am loving this to the point that I'm going to use it on the first one, even though I don't need to. Which, yeah, let's put that there. Grow growths. The 2 arguments got none on growth end. Not at the end of the growth, but on grow, it'll be max, well, lock, and then it'll be max y equals math.max max y lock dot height. There we go. And yeah, we don't need to do growing anymore. So max y and number was 0, so it's a 0. Then we return max y. Again, part 1 doesn't need to do all this, but I like reusing my cool function. That's right, we don't need to make a location here. I am loving it. I'm not going to shove it straight in there. It's good enough. So we have our growths, we have our visited, we have our cool function that does some stuff. We love that. Dijkstra, hello. Here's the one I want to do. I wanted to split these into 2 different functions. That's one of the reasons I made that parameterized. Add lock to main trunk. Track main trunk rather. And then that bit doesn't, it's conditional. Which means it can live with its own piece of data. Don't you love it? Yep, so we have leaves, cost add leaf, goes lock, leaves, add lock to key lock. So boom, we have the addition of the leaf, the addition of tracking the main trunk, and we have adding locations to visits. All up there, the generation of the graph and the distances, which is important, and the actual finding of the smallest. I think that was it. I think that is as far as I'm going to get this refactored. And it works like a charm, so let's put that in. 1.4 solution. And I am going to call it there. Well, I'll call there after I walk through my solution. Nearly forgot. So, solve quest 1. I already walked through the challenge, but first thing we do is we parse all of the growths. So for every line, we split it up by a comma, because that's what we're given. We figure out the direction, and we figure out the number of how many you want to go in that direction. The direction is one of these 6 characters. The number is always a number. Based on that direction, we return location change, which is just a location where everything is 0 except what's changing. So if you're going up, then your height is going positive. If you're going down, then whatever you said is your height negative. Same for right, left, and forward, backward. Next thing we do is we call our super cool function, which based on what you're trying to solve, you can do different things with. But the main core of it is that it grows the growths. So for every growth, it starts at 0, calls some event listeners, basically. And for every change of it, it goes through all 3 of the keys, which is x, height, and depth. It's like, okay, how many did you want me to go in this new direction? How many times did you want me to go? And then it does that many times, modifying x, height, or depth by 1 or -1, depending on the direction. And then, of course, calls our listeners again if they need to do stuff. And finally, at the end of the growth, it calls another listener if you needed to do something there. For solve 1 in particular, we needed to update the max y. Update max y. There we go. Let's make this a little easier. So basically every time it grew, we needed to just set the maximum y, or the maximum height we've ever been to the maximum height we've ever been to. Which I'll rename that right now. So yeah, we define that. We call our growing of growths every time it grows in any direction at all, in the slightest. It sets max height to either max height or the current height for this location. This is technically unnecessary for the first part. There was a more optimal way before it, but it wasn't really reusing as much of this functionality, so I did it this way because I like it this way. Quest 2, relatively similar, still using all the same things, but this time we're keeping track of everywhere we visited. So every time it grows, we're like, hey, take that location and remember it. So we add that to a set of strings, a little helper function that turns a location into a string by just joining the different pieces together with this unique character. We also have this function that does the inverse, but we don't use that into part 3. Speaking of part 3, first we do 3 things that we want to track for all the things that are happening. First, we want to add a location to visited. That's not new. Then we want to track all of the main trunk locations. So basically, if you are adding a segment to somewhere that is, well, x0 and depth 0, you can see that. We want to keep track of those because those segments there are the only ones we can tap for syrup. So we need to keep track of them. We could just go back through visited and extract them out, to be honest. So yes, we could save memory a little bit just to spend the exact same memory later, but I didn't like it. And then for leaves, basically at the end of a growth, that is considered a leaf position, so we're just keeping track of those. Very similar to adding location to visited, just to a different set. Finally, since this is a bit of pathfinding, we are using Dijkstra's again. So we need to generate a path that is every way you can go from every position. So we go through the from key, we generate an array of places you could go. This is a little trimmed down because unlike a real Dijkstra's, there's no actual weighting here. This is just distance where they're all 1, so probably didn't even need to use Dijkstra's. Could use something much dumber, but I could copy Dijkstra's from yesterday's solution, so that's what I did. Here's where we actually generate it. So the trick here was that we wanted to find the shortest path from each trunk to all of its leaves. Now there's like a couple hundred trunks, but there are less leaves than that. So for each trunk, if I would have ran Dijkstra, it would have looked at all 6,000 places, and then would have been able to look at my 20 or so leaves. But that's like, let's say 200 runnings of Dijkstra on this data set versus 20 runnings of Dijkstra, because there are like 20 leaves on this data set. The same information is available in both, but this where you do a lot less generations. So instead of going from the trunk to the leaves, we're going, hey, for this leaf, let's see where you could have made it. And then once we generate that, we use it by saying, okay, I am this trunk key. From the leaf I'm trying to figure out how to get to, instead of me going to the leaf, let's see how long it took the leaf to come to me. Because directionally it doesn't matter, we just care about the distance. So the direction of who's from and who's to ain't mattering. So we did that. We have a little early break here to save a couple cycles. That's it. That is the end of part 3 here. So, as always, hope it has been a pleasure, because this was a fun one, and I can see this being a fun one to visualize too. Yeah, that is it. Till next time.